Hello, everyone. Today, I'd like to talk about the application of flavins in photoenzymatic catalysis. Flavins has been historically used widely in organic syntheses as photocatalysts. And today, I'd like to focus on their usage in photoenzymatic catalysis. More specifically, I'd like to share with you Professor Todd Hyster in Princeton's work in this field. Now, these are the contents. First, I'd like to introduce you about what flavins are and the modes of reactivity, especially in terms of redox. Next, I'd like to share you about Professor Hyster's chemistry and how they started and how this study progressed so far. And lastly, I'd like to summarize and finish my video today. So let's get started. Flavins are compounds with a isoalloxazine or a alloxazine core, which is shown at the right-hand side. There are some naturally occurring flavins, and the most famous ones are riboflavin, FMN, which stands for flavin mononucleotide, or FAD, which is known as flavin adenine dinucleotide. The structures are shown at below. And generally speaking, FAD is more common than FMN. And also, diazoflavins, which lack a nitrogen at the 5 site, are also known. And especially in nature, there is a compound known as coenzyme F420, which is a diazoflavin. Now, next, I'd like to share about the modes of flavin reactivity. Since I'm focusing on photoredox chemistry today, I'd like to just briefly share with you about how flavins behave in redox neutral manner. But speaking of that, flavins are also widely used in these redox neutral catalysis. So first, with a reaction with the nucleophile, hard and bulky nucleophiles tend to attack the 5 nitrogen, which is shown here. And soft nucleophiles, like such as acetates or thiols, tend to attack this 4A carbon. And for the reaction with electrophiles, usually most reactions occur at the number 5 position nitrogen, and rarely some reactions occur on the aromatic ring. Now, for the redox chemistry, flavins are widely known for their reversible redox chemistry. So as you can see here, the most oxidized flavin shown at the left can accept 1 electron and form a flavin semiquinone. Then another electron acceptance will lead to the flavin hydroquinone. And this process is completely reversible in aqueous solution. First, I'd like to share about mediating oxidation using flavins. So the most common active oxidant is the C4A hydroperoxide of flavin. So these structures are shown at the right-hand side. You can see here, they're just like protonated forms. So how they form, there are mainly 2 pathways of formations. So you can start from the flavin hydroquinone, or you can just start from the neutral flavin. When you start from flavin hydroquinone, you have to oxidize 2 times, which means you have to transfer 4 electrons. And oxygen, molecular oxygen, is the right oxidant for that. So as you can see, following this process, which undergoes the radical process, will generate this C4A hydroperoxide anion. On the other hand, if you start from just neutral flavin, you can use hydrogen peroxide, and you can just add into this imine, which will lead to this adduct. These C4A hydroperoxide adducts are generally unstable, and the hydrogen peroxide tends to eliminate. However, these adducts are readily stable in enzymes, and this is due to the active site coordination, which kind of like holds on to that nitrogen basicity, which is the main factor of elimination. Now, this is a general scheme of how flavin C4A hydroperoxide is used as a oxidant. There are various oxidation reactions catalyzed by this C4A hydroperoxide. And One of the most famous ones are amine oxidation or the Baeyer-Villiger oxidation. As shown previously, the popular oxidants are like molecular oxygens or hydrogen peroxide, but a few others can be used. So if you remember the scheme I showed previously, when you use molecular oxygen, you need to reduce the flavin to the flavin hydroquinone. So in that process, you need a appropriate reductant. So various reductants can be used: hydrazine, ascorbate, formate, hash ester, zinc. But I'd say the most popular ones, especially in biocatalysis, is NADPH or sodium dithionite. Now I'd like to talk about flavin oxidations in nature using flavins. Basically, there are like two types of flavin oxidation, which is one is flavoprotein oxidase, and the other is flavoprotein oxygenase. So these two differ by the oxidases just perform a formal oxidation, whereas oxygenases perform a formal oxygenation. So you add a oxygen atom. So these two enzymes are all mostly FAD or FMN dependent. And for the flavoprotein oxidase, which just does the oxidation, the active oxidant is usually the flavin, which is the oxidized quinone form. And they are generally classified in 6 families. And you can like generalize their mechanism shown here, which is a very generalized. Some enzymes don't work like this, but this is the most general and common way these enzymes work. So this hydride kind of like acts as a hydride leaving group and transfers to the flavin. The other hand, flavoprotein oxygenases utilize the C4A hydroperoxide that I've shared with you previously, and this serves as the active oxygen source. So the reaction shown here is a Baeyer-Villiger oxidation, which is a oxygenation, and this is also catalyzed by a flavoprotein. Another example is the sulfide oxidation, and there are a bunch of other oxygenation reactions that these flavoproteins can catalyze. There are about like 250 members currently reported, and they are characterized into 8 different groups. Now I'd like to share about the reduction reactions using flavin. Unlike the oxidation reactions, there are no significant small molecule reactivity for reduction. However, flavin-dependent reductases are very well known, and especially ene reductases are most well characterized and widely used. Ene reductases are, as you can see from its name, they reduce a ene, which is a double bond alkene. These alkenes are usually activated by electron withdrawing groups, and not all of these enzymes are flavin dependent, but mostly they are. And they're divided into 5 classes. And the old yellow enzyme, which is abbreviated as OYE, are most predominant. So mechanistically, you can see here in the left-hand side below, the electron withdrawing group conjugated alkene gets like some kind of Michael addition like hydride attack and subsequent protonation to formally reduce the double bond. Now I'd like to talk about the OYE, old yellow enzyme, in more detail. Old yellow enzymes, since they are ene reductases, they do reduce alpha beta unsaturated carbonyls, and especially they have higher selectivity and reactivity towards the more activated ones, such as aldehydes, ketones, esters, kind of borderline, lactones pretty good, amides not so good. It behaves like that. And structurally, they have a tin barrel motif that binds to a FMN, so they use FMN as cofactor, not FAD. mechanism-wise, the hydride from the flavin hydroquinone first attacks the alkene in a very scarce, selective, asymmetric type, a microaddition type, and then the subsequent protonation from the tyrosine, which is at the opposite side of the flavin, generates a reduced product. So this is a very trans-specific reduction. These enzymes are very widely used in industry, and they are very promiscuous. They can mediate a bunch of different reductions and generate very useful chemicals such as nylon 6 precursors, terpenes, citronellals, and a bunch of many more. Another ene reductase class I like to share about is the enoate reductases. These reductase family has 3 cofactors. One is the iron sulfur cluster, 4 iron, 4 sulfur. The second one is FAD, and the third one is FMN. Due to their highly sensitive nature towards oxygen, the mechanism is currently unknown. And what's pretty interesting is that they have a marked preference for poorly activated alkenes. So they react much better with poorly activated alkenes, such as like alpha-beta unsaturated acids or esters, amides, those things. They don't react well with aldehydes or ketones. They're evolutionary related, but structurally and, as you can see, functionally, they're pretty distinct from all yellow enzymes. So the structure shown here is a AlphaFold 3 structure of a enoate reductase I've drawn. And you can see there are 2 flavin binding sites, and between there, you can see the 4 cysteines kind of like positioned in a tetrahedral manner. So I proposed that iron sulfur cluster would go in there. So what I think is that this flavin here, I'm not sure if it's a FAD or FMN, but the right flavin pretty looks like the OYE active site. You can see the flavin here, the tyrosine here, substrate comes between, this histidine forms a dyad for binding. So I'm pretty sure this should be FMN because I think it's related to the OYE site. So this flavin will receive electron, and then it will transfer this electron to the iron sulfur cluster here. And subsequently, this will be transferred to the FMN. And I propose that these methionines here would mediate this electron transfer process. But that's just my speculation. I have no evidence. But yeah, that's that. And let's move on. So next, I'd like to share about the modes of flavin reactivity in terms of photochemistry. Generally speaking, flavins, the oxidized forms, are visually yellow, and they have absorption at 260, 380, and 450 nanometers. A singly reduced form, which is a semiquinone, have a maximum absorption around 500 to 600 nanometers when it's a neutral, which is blue, or when it is deprotonated, it becomes red, and it has absorption at 380 and 450 nanometers. The most reduced form, which is the hydroquinone, has nearly no significant absorptions in the visible light region, maybe near 400, but not so much than the other 2 flavin forms. So naturally speaking, there are only 3 flavin enzymes that are known to utilize the photochemistry, and the 2 among those 3 are DNA photolyase and fatty acid decarboxylase. The other one mediates biosynthesis of chlorophylls. So these 2 reactions all utilize light, but you can see DNA photolyase as a mediator between, whereas the fatty acid decarboxylase utilizes light directly. So it's pretty, I'd say, astonishing that photochemistry is not that widely utilized in Mother Nature, and I suppose there should be some kind of reason behind that. And lastly, I'd like to just share you about some physical chemistry numbers, which is the electron reduction potential. So the reduction potential of FMN hydroquinone is minus 0.45 volts for SCE electrode. However, if flavin hydroquinone is photoactivated, photoexcited, the reduction potential goes lower to minus 2.26 volts, which is much stronger reductant. Now I'd like to talk about the Hyster group chemistry. The initial discovery of photoenzymatic reduction via single electron transfer was, I like to say, these two papers. The first paper, which is the Jack's paper shown at left, has demonstrated that flavin hydroquinone can mediate a reduction via single electron transfer. However, this is not a photo redox process. It's just ground state single electron transfer, hydrodebromination. The paper on the left-hand side, which is the right-hand side, which is from Angewandte Chemie, is a reduction of a ketone using flavoprotein ene reductase. But in this reaction, they have used ruthenium photocatalyst to generate the active radical. So it's not like a pure bio-photocatalytic reaction. So the general schema of Hyster group chemistry, it's shown here. So first, you start from the flavin hydroquinone, and at the active site, the radical precursor and the coupling partner binds. These two molecules can be a same molecule, so it's like a intramolecular process, or it can be different. They form a charge transfer complex by some like pi-pi interactions with the flavin. And as you shine light, a single electron transfer from the flavin to the radical precursor happens. Then after mesolytic cleavage, you generate the radical. And this radical couples with the coupling partner, generating a coupled radical. And then this radical will receive another electron from the flavin semiquinone by not just a radical, but in form of a hydrogen atom. So it's a asymmetric hydrogen atom transfer. Then the product is removed and flavin is reduced back by sodium bithionite or NADPH. So this is how the Hyster group chemistry generally works. And generally speaking, this chemistry is composed of mainly three factors. One is the radical precursor. The next one is the acceptor, which is the coupling partner. The last one is the quenching method. The process I've shown previously utilizes a reductive quenching method using hydrogen atom transfer, but other methods such as oxidative processes using beta scission or radical polar crossover to generate a carbocation was also realized. So I'd like to share some papers of how these chemistries have been worked out, and more specifically for these acceptors. Now, the first paper I'd like to share with you is the Science paper from 2019. So this reaction, this paper utilizes a E-reductase to generate this cycloamides from alpha chloroamides by intramolecular radical cyclization. As stated previously, the reduction potential, the half potential of the FMN in ground state is minus 0.45 volts. However, after photoactivation, photoexcitation, the reduction potential becomes minus 2.26 volts, which is enough to reduce the alpha chloroamide, which has a reduction potential of minus 1.65 volts. Screening a bunch of heme reductases yielded that the GLU-ER, the gluconobacter oxidase E reductase, and the OIE1 enzyme was the most efficient. And these two enzymes had opposite enantiomer selectivity. Then, when they have screened a bunch of different wavelengths, they have found out that 490 nanometer cyanide was the most efficient. And lastly, they found that a T36A, which is a mutation from threonine to alanine at number 36, was most efficient. As you can see here, it'll become 68 to 89%. And you can see this site is right here, which is pretty distant from the active site. And the authors are not sure how this mutation was affecting. Now, these are the substrate scopes. A bunch of different substrates. Cyclization modes are investigated and probably expected, but GLU-ER T36A was not always the best. So you can see 6-member ring, 7-member ring, 8-member ring were be made with pretty good ER with somehow acceptable yield. And also, this reaction generates 2 new stereocenters at most. So the diastereomeric ratio, DR, was also observed, and you can see in terms of diastereoselectivity, at the lower row, you can see they're all pretty acceptable, good. Now, the authors have dived into the mechanism behind this reaction. So first, what they performed is a UV-vis study to reveal the formation of a charge transfer complex. As you can see in the figure A, the blue line is the UV-vis spectra of just the enzyme. And as you add the substrate, you can see there is some kind of bulge peak around at 490, 500 nanometers, which is showing the formation of the EDA complex, the charge transfer complex. Next, the deuterium incorporation experiment showed that hydrogen atom transfer is from FM and not from surrounding solvents or other side chains. And lastly, they have observed alkene geometry dependence, but as you can see, E isomer and Z isomer, so down here, E isomer and Z isomer, they both show the same diastereomeric selectivity, which means that enzyme stereoselectively likes a certain intermediate structure. However, you can see the Z isomer's selectivity is much worse than the E isomer, and this can be thought because of the bond rotation process. So what you can know is that the bond rotation is competitive with the hydrogen atom transfer process. The rate is pretty comparable. So that's why you see the same diastereoselectivity, but worse for one isomer. The next reaction the authors have performed is a radical clog experiment, which they tried to support the radical mechanism. So as you can see here, they used a cyclopropyl phenyl alkene, and after the reaction, they have observed no cyclopropyl ring, which means that the hydrogen atom transfer rate is much, much slower than this ring opening process, which has a rate constant of 6.1 times 10 to the 4. However, the subsequent process, which is another cyclization, shown here, seems to be comparable because the two products, the uncyclized one and cyclized one, have both been isolated. So this cyclization rate is probably comparable with the rate of hydrogen atom transfer. What the authors have also observed is the rate dependence of this reaction against the flux of light. So the observed total cat rate is proportional to the photon flux of the light source, which means that that's the rate determining step. But what's interesting is that the Km value observed from these two different fluxes were pretty similar. And this states that using this equation, it's a pretty rough equation, but using this equation, this kcat is different for these two setups, but since Km is similar, what it implies is that K minus 1 is much, much larger than kcat. So that change in kcat doesn't make significant change in Km. And this means that the substrate binding is highly reversible. I'd like to talk about another paper, which is utilizing the cyclization of iodoalkenes. So the difference between this paper and the previous one is that the previous one, the alkene precursor, was a alpha chloroamide, which is a rather activated substrate. However, this JAX paper uses a iodoalkene with no significant activating groups. And you can see the reduction potential of just normal iodoalkene is around minus 2.19 volts, which is much lower than the alpha chloroamides. And just looking at by the numbers, you can see FMN, once photo excited, it's enough to reduce the substrate. So the authors have just gave a shot. And they found out that after a bunch of in reductase screening, GLUE-ER, which was the same enzyme shown previously, and the OIE2 showed the best yield and enantiomer selectivity, and they had opposite enantiomer selectivity. So what's significant for this paper is that the reaction, as you can see here, the enoate cyclizes with a pendant iodoalkene to form a 5-membered ring. You can see the final hydrogen atom transfer occurs at the alpha 2 carbonyl position. And what's important is that the native reactivity of these in reductases is that, as shown in the right top side, is that the tyrosine from the opposite side donates a proton to formally reduce this double bond. So one can suspect that this tyrosine will also be able to donate this hydrogen atom to this carbonyl alpha position, which will lower the enantiomer selectivity. And this was proven to be true by mutating this tyrosine to phenylalanine, which has improved both ER and yield. And also, since this is a radical reaction, the degassing of solvent was also beneficial. Mechanistically, they have also observed the formation of this EDA complex, charge transfer complex, which I'd say pretty normal. And also the deuterium incorporation experiment showed that this hydrogen atom is coming from the flavin. As I stated previously, the significance of this reaction is that the steric selectivity is reversed from its natural function. So the natural function delivers the alpha hydrogen to the prochiral center from the tyrosine side, which is opposite from the flavin. However, this reaction, the hydrogen atom is transferred from the flavin. So obviously they will generate different stereoisomers. And lastly, a radical clock experiment using cyclopropyl fused alkene showed that this hydrogen atom transfer process is very quick because the cyclopropyl ring was like half open and half still closed, which corresponds to a rate constant to 10 to the power of 8. What the authors have also tried was using NHPI esters, which is N-hydroxyphthalimidyl esters, which are comparably reactive to iodoalkanes, and they're widely used in, let's say, electroorganic chemistry, organic chemistry to generate radicals. And as you can see here, they were pretty much reactive to generate 5-membered, 6-membered rings. And also, instead of just terminating by hydrogen atom transfer, they have used a pendant alkene, which somehow resembles the substrate from the Science paper 2019 shown previously, to perform a cascade cyclization to form 2 5-membered rings, which I think is pretty cool. Now I'd like to share about the chemistry using a nitronate as an acceptor. So nitronate is a functional group shown here. It's a conjugate base of a nitroalkane. So the process, simply this serves as a acceptor, generates this radical anion. And if this intermediate undergoes a mesolytic cleavage followed by hydrogen atom transfer, like the previous chemistry, it will generate this reduction product, which is just a formal CC bond formation. However, when the radical goes back to the Flavin semiquinone, which is a radical polar crossover process, it will generate this nitroalkane, which is a redox neutral process. And these two chemistries were all realized and reported, the reduction process in Nature. And the redox neutral process in Yes. So I'd like to share about the reduction process chemistry, which was reported in Nature. So when the authors screened a bunch of enzymes, they found out the GluERT36A mutant and CSER, Caulobacter cygnus reductase, was most efficient. And also this time, these two showed opposite enantiomer selectivity. So they decided to go with CSER because it showed much better yield and ER. So the key thing here is that the acceptor, the nitronate, is a conjugate base of nitroalkane. So in order to maximize the concentration of the nitronate, you have to make the solvent, the condition, as basic as possible so that you can push all of the nitroalkane to the nitronate. So the initial screening was performed in pH 8, which yielded like 28% yield. However, when they conducted this reaction at pH 9, this yield jumped up to 92%. So as you can see, the overall chemistry is ligation between this alpha chloroamide and the nitroalkane to this ligated product. But one thing that's worth noting is that chloroamide's reduction potential is minus 1.65 volts, whereas the nitroalkane, specifically nitroethylbenzene here, the reduction potential is minus 0.89 volts. So nitroethylbenzene should be a better substrate for reduction, but this chemistry works, and obviously it should only work when chloroamide reduces first. So this is kind of puzzling. So the authors have decided to investigate how this was possible. So I'd like to share you in the next slide. So what they have found out is that when they check the UV vis spectrum, they have observed this feature of two broad peaks when they mix the enzyme and the nitroalkane, not the alpha chloramide. And the author suspected that this feature is due to a small percentage of oxidated flavin generated by this nitronate, which should be there because of the redox process with the nitronate. But what's pretty interesting is that they have observed no reduction product from nitronates, such as like hydroxylamines or nitrosyl compounds, amines. They have just observed none of them. So what this implies is that this nitronate forms like some kind of complex and with the flavin, with the flavoprotein, the reductase, and does undergo a single electron transfer, but this process is reversible and it just stays like that. And once the substrate, the other substrate, the alpha chloramide goes in, then the irreversible ligation process just goes on and generates products. So in order to observe the charge transfer complex, they obviously, if they use nitroalkane, then it will, you can see this mode of absorption here will interfere the analysis of formation of charge transfer complex. So they somehow had to remove this. So what they tried was using a nitrone. Nitrone is shown the right-hand side here. It's it looks pretty similar with nitronate, but instead of oxygen, one oxygen, there's a alkyl group, carbon right there. So nitrones are less reactive than nitronate, and they don't form this reversible single electron transfer complex. So that, but they are still reactive enough to form this ligation product with the alpha chloramide. So they use this and observe the charge transfer complex around at 480 nanometers. Another hypothesis that can be said is that the formation of this reduction process product, it may occur via mesolytic cleavage and hydrogen atom transfer, but also it can occur by a radical polar crossover, generating this nitroalkane first and undergoing a 2-electron reduction process, 1 electron, and generate the product in the same manner. So in order to confirm this, it's pretty easy. You just mix this guy, the nitroalkane, with the enzyme and see if you see the generation of the product. And fortunately, they did not. So it shows that it's a mesolytic cleavage hydrogen atom transfer process. And also this pathway was supported by DFT calculations. Now I'd like to share you about some notable endeavors from the Hyster group to perform this bunch of Flavin biocatalysis reactions. So the first, before going in, I'd like to share about the major side reactions of these photocatalytic Flavin chemistry. The major side reactions are hydrodehalogenation of substrate, but that's not like a big issue with the enzyme. The major issues is that first, it's the amino acid alkylation, since the substrate is a good electrophile with like alpha chloramides, iodoalkanes. They are just excellent electrophiles. And also they can alkylate the catalyst FMN, which was obviously being observed. So they nice enzyme optimization platform and a better utilization of lights with longer wavelength was needed because this alkylation processes were mediated by light. They were photomediated. So using a lower energy light was it should be beneficial to suppress the side reactions. And the mediated alkylation of FMN is shown here. And it's just pretty straightforward, so I won't talk in detail. The first paper I'd like to share about is the setup of a high throughput optimization platform of photoenzymes, which was published in Angewandte Chemie 2022. So the main challenges in this optimizing photoenzymes in high throughput is, first, it's difficult to achieve uniform irradiation. Second, it's kind of related, but there's crosstalk between wells, so the light shining for one well may also shine the neighboring wells. And lastly, there are thermal differences because light also generates heat. So what they've optimized, they achieved using white well with a white opaque well with individual lighting and adequate cooling, which you can see here, cooling with fans from the top. So using this platform, they have optimized the original chemistry, which is the Science 2019 alpha chloramide intramolecular cyclization reaction. So this optimization has, using the error-prone mutagenesis, they have generated a mutant called GluERG6, which was 6.3% quantum yield, which is what's originally 1.5% for the wild-type GluER enzyme. And moving on, they have found out they have characterized other mutants which were optimal for other modes of cyclization. So they have achieved and shown that this platform can be used in a high throughput manner to optimize photoenzymes. Next paper I'd like to show you is the conjugation of a light harvester to the enzyme to better utilize light. So far, all the lights utilized were cyan lights, which were 494 nanometers. But the main issue is that the enzymes were not so, the quantum yield is low, and you can also see that the extinction coefficient was 3.6 times 10 to the power of 3. It's not that bad, but it could be better. It's pretty low for a photocatalyst. So they've decided to conjugate a dye, specifically atyl dyes, which are shown in the right-hand side. And chemistry-wise, they performed a linkage with sulfur-lysine. So they have found out that conjugating these light harvesters, which the atyl 565, which is the yellow one, turned out to be the most efficient one, but they all shown that they could absorb light much better with extinction coefficient of 1.2 to the 10 to the power of 5. And that could also be shown by the decreased lifetime, the fluorescence lifetime of these atyl dyes. When they are non-conjugated, their lifetime is 3.75 nanoseconds, but it decreases to maximum 0.63 nanoseconds, which is pretty remarkable. And it shows that the energy is additionally being transferred to the flavin, which corresponds to the energy transfer efficiency of 80%. So this transfer energy has been obviously utilized to conduct this cyclization reactions or ligation reactions. As you can see, these enzymes were much more superior than the GluERT36A mutant, which were originally used in green light. So in green light, the original enzyme was like 90% for the cyclization, but whereas this conjugated variant is like 85% for. And what's more impressive is for the intermolecular hydroalkylation, the ligation reactions. You can see the right-hand side. The original enzyme was like less than 1% yield, but this enzyme performs like 51% yield in green light. So that's It's crazy remarkable. This is a nice method of utilizing a longer wavelength light. And what's much more remarkable is the following paper. This paper is not yet published. It's uploaded in Chem Archive. And this chemistry utilizes red light. It's from cyan to green to red. So the hypothesis of the authors is that fine-tuning the active site will optimize the binding between the substrate and the Flavin catalyst, which will eventually lower excitation energy of the charge transfer complex. So they have screened a bunch of different enzymes and found out glue ERG6 mutant, which was obtained in the Angewandte Chemie paper I've shown previously, was the most optimal. And they performed further mutations using a machine learning based program called MuteCompute, and found out that glue ERG6 and then T36E X118C mutant was much better performing. And lastly, for enzyme stability improvement to suppress side alkylation, they have mutated the lysine at 283 position to glycine. And that final mutant enzyme has shown 29% yield in low light intensity and 99% yield in high light intensity in red light, which is just uncomparable with the original glue ERWT wild type enzyme. So the authors have performed a computational study, multi-configurational paired DFT, and found out that the cyan region absorption is from the excitation of within the flavin. However, this new absorption in the red region is from the energy transfer from flavin to a LUMO, which consists of both flavin and the substrate. So it's much better electron transfer. And also MD simulations have shown that these mutations found in the front slide has reduced protein flexibility and solvent accessible surface area, which seems to have led to a better result. And by docking, what they have found out is that maximum distance between pi systems has decreased, and while the minimum distance increased between the substrate and the flavin. So it implies that the pi systems between these two compounds are much more parallel. And also in red light, the cofactor double alkylation side reaction was completely suppressed, which was a major side reaction in cyan light. So this result is pretty remarkable. Now to summarize, today I've shared how photoexcitation of flavins enables a natural radical chemistry, and also, especially in Hyster's group chemistry, a wide variety of radical precursors and acceptors were realized. And I've also like to share with you how the Hyster group has approached and designed these photoenzymatic reaction systems. And also lastly, the strategies for better harnessing light. However, there are some limitations, which are enzyme deactivation, alkylation issues, substrate solubility, scalability, because this is a photoreaction, there are too much variables. And lastly, reactivity scope, it's still not broad enough for general synthetic applications. Yeah, so this is it for today, and I hope you enjoyed, and like and subscribe. Thank you.